Welcome to the High Voltage AI podcast. This is Thursday's deep dive in our week-long series, which you can also find in the High Voltage AI newsletter over on Substack. This whole week, we're really focused on helping electric utility engineers like you get up to speed on, well, critical power system concepts. Now, our broader series often covers topics like overhead and underground construction types, why we use them, their different characteristics. But today, we're zeroing in specifically on grid forming tech. The topic is real-world applications, from Australia's mandate to Texas storage. We're going to look at how this technology is really moving beyond just theory. It's becoming a proven, really transformative solution around the world. Okay, let's unpack this.
Yeah, it's actually fascinating, isn't it? Just how fast these ideas are moving from, the lab or the research papers into actual large-scale use. So our mission today is basically to pull out the key insights from these real-world deployments. And why does this matter for you? Well, understanding these applications shows not just what can be done, but crucially why it's so important for the future grid. We're talking resilience, efficiency, integrating more renewables. We'll look at how different places are hitting really high renewable numbers, improving stability, getting economic benefits, often through mandates, sometimes through clever market setups.
Right. And just to give everyone the full context for the week, on Monday, we started with grid forming versus grid following, those fundamental differences. Tuesday was all about control system architecture and how synthetic inertia actually works. Yesterday, Wednesday, we tackled system integration challenges, things like protection, coordination, grid codes. And today, the real world stuff. Then tomorrow, Friday, we'll shift gears a bit and look at career opportunities and the kind of power electronics expertise needed in this grid forming era. Okay, so let's kick things off down under. Australia, specifically South Australia, feels like it's become this huge real-world grid-forming lab. They've had a massive transformation. I remember that big blackout back in September of 2016. That seemed to be the real trigger, right? Can you walk us through how that crisis really sparked all this innovation?
Oh, absolutely. That blackout, it wasn't just a blip. 1.7 million people lost power. It was the definite catalyst. It pushed them into this incredible sprint from crisis to innovation between roughly 2016 and 2025. And they didn't just react, they put in place some really specific, quite forward-thinking technical requirements. You mentioned the Australian-New Zealand standard 4777.2, the 2020 version, that made grid forming capability mandatory for new battery storage over 5 megawatts. That was huge. Plus, they set minimum system strength requirements, needed synthetic inertia, demanded really fast, like sub-second frequency response, and even autonomous voltage regulation. So systems could manage voltage without needing a signal from the wider grid. Pretty comprehensive stuff.
Wow, mandatory above 5 megawatts. That's quite a statement.
Okay.
How did they manage the actual build-out? The infrastructure side must have been a challenge on that timeline.
It was definitely ambitious, but they moved fast and strategically. The Hornsdale Power Reserve, that 150 megawatt, 194 megawatt hour battery, that was sort of the poster child early on, showcasing the grid forming capability. But it goes way beyond that now. They've got about 2.7 gigawatts, 4.5 gigawatt hours total of grid scale battery capacity, all required to have these grid forming features. And it's not just the big stuff. Think distributed resources, too, over 40,000 home batteries with smart inverters, plus over 50,000 resources like solar and batteries coordinated in virtual power plants. It's a multi-layered approach.
That scale is really something. So with all those requirements and that level of deployment, what did it actually do for the grid? What were the performance results? Did it deliver?
Oh, it delivered, and then some. The results are pretty compelling. For system stability, they saw a 50% drop in major frequency swings, those events bigger than plus or minus 0.15 hertz. So a much calmer, more stable grid. Renewable integration. The whole national electricity market is averaging, 68.7% renewables now? In South Australia itself, it's at 93% instantaneous renewable penetration at times.
93%? Wow.
Exactly. It shows grid forming really unlocks that high renewable future. Economically, they're saving over 200 million Australian dollars annually just on frequency regulation costs. That's real money. And reliability of the SA80 metric, System Average Interruption Duration Index, it dropped from 155 minutes back in 2017 down to just 45 minutes by 2024. So fewer and shorter outages.
45 minutes? That's a massive improvement in reliability. It makes you wonder, how did they pull that off? Especially dealing with grid strength, which is always a challenge, and getting it all to work with the market. What were the key innovations there?
Grid strength was definitely a focus. They got clever. They didn't just rely on batteries alone. They used what they call dynamic system strength. So they paired traditional synchronous condensers. They've got four 35 megavolt ampere units, providing that spinning rotational inertia as a backup with the grid-forming batteries, which act as the primary source of synthetic inertia and voltage support. It's a hybrid approach, managed in real time based on what the grid needs moment to moment. Very dynamic.
Okay, that hybrid approach makes sense. But what about the market side? Incentivizing these new services is often the tricky part.
Crucial point. They actually created a whole new market category, essential system services. This specifically pays for inertia, system strength, and operating reserves, and the payments are tied to actual performance, how well a resource actually responds to frequency deviations. They even use locational pricing, paying more for services in weak parts of the grid where they're needed most. And importantly, it's technology neutral. Synthetic inertia from a battery competes directly with rotational inertia from a synchronous condenser. Operationally, they learned quickly that these batteries are just way faster and more accurate for frequency response than old thermal plants. Plus, you can actually dial up the synthetic inertia during stressful grid conditions. You can't really do that with a traditional generator. And interestingly, instead of making things more complex, this combination of storage and renewables, managed well, has actually led to more predictable system operation. They're using advanced controls to operate safely, closer to stability limits, and they figured out that the minimum system strength needed is basically a function of load, how much renewable power is being generated, and how much grid-forming capacity is online. It's a whole system view.
That Australian story is just really powerful. So how does this compare? Here's where it gets really interesting. How does this compare to other regions? Let's jump over to Texas. They've also had this explosion in battery storage. What's driving ECOT's storage revolution? Is it different from Australia?
Very different drivers, yes, but equally impressive results in terms of deployment speed. Texas has seen just incredible growth, over 5 gigawatts deployed, and something like 4 gigawatts of that came online in 2024 alone. That's staggering. A lot of it is lithium-ion, concentrated where there's lots of wind and solar, and providing these enhanced grid services. But unlike Australia's mandates, Texas is almost purely market-driven. ECOT, the Electric Reliability Council of Texas, runs an energy-only market. That means prices can swing wildly. Storage thrives on that volatility, charging low and selling high. Plus, there are really valuable ancillary service markets, frequency regulation, reserves that pay a premium for the fast, accurate response batteries provide. The market signals are just right.
So, market forces really pushing it there. Okay, how does the performance stack up? What's the validation telling us about how these Texas batteries compare to traditional generators?
The performance data from Texas is, frankly, stunning. Frequency response time, average 150 milliseconds.
Yeah.
Compare that to 10 seconds or more for a traditional thermal unit.
Huge difference. Massive. Accuracy, plus or minus 0.1% for frequency regulation. Traditional resources might be plus or minus 0.5%. Availability is higher too, like 98% plus versus maybe 85-90% for thermal plants. Yeah. And ramping, they can go from 0 to full output in under a second. Conventional plants take minutes. It really shows that grid-forming storage isn't just filling a gap. It's providing a fundamentally better stability service. We saw this vividly during Winter Storm Elliott back in December 2022. ERCOT lost about 14 gigawatts of generation almost instantly. Grid-forming storage was absolutely critical. It managed that massive loss without triggering widespread blackouts. Batteries provided something like 70% of the primary frequency response and crucial reactive power to prevent voltage collapse. And that grid-forming capability also meant faster system restoration black start afterwards. It proved its worth in an extreme event.
That's incredible. Surviving that kind of event really validates the technology. What about the economics in Texas? Has all this storage actually saved money or generated value? Definitely. There was an analysis by the American Clean Power Association. They found Texas storage has saved over $750 million in wholesale electricity costs since just 2023. It's pushed down peak prices by 40 to 60% in some cases. And by placing these batteries strategically, they've avoided potentially over $2 billion in transmission upgrade costs. That's a huge saving on infrastructure. Plus, the batteries themselves are earning over $300 million a year just from selling those ancillary services we talked about. So yes, significant economic impact across the board. It's a clear win-win.
Wow, avoiding $2 billion in T&D costs, that's a major benefit utilities need to consider.
Are there other innovative applications happening in Texas besides just the big grid-scale batteries?
Oh yeah, absolutely. Virtual power plants, or VPPs, are a big deal there. They're aggregating over 500 megawatts of distributed storage, think home batteries, commercial building batteries, and coordinating them as a single resource. The Tesla VPP is probably the most famous, pulling together like 10,000 home batteries. They use sophisticated machine learning to optimize how all these distributed resources respond to grid needs. And then you have these major transmission-connected projects really pushing the envelope. You mentioned Moss Landing earlier. That's technically in California, but it's a key example. 400 megawatts providing grid-forming services to CAISO. In Texas itself, you have projects like Gateway, 230 megawatts helping integrate wind power, Crimson, 350 megawatts for firming renewables, and Gambit, a 100-megawatt project specifically demonstrating advanced grid-forming controls. So lots of innovation to different scales.
Okay, so we have Australia's mandate-driven success, Texas's market-led boom. What does this mean globally? Are other places catching on? How are they adapting this tech?
It's definitely a global phenomenon now, with different regions tailoring it to their needs. Look at Europe. Germany's Energiewende, for instance. They've got, over 60 gigawatts of distributed solar PV, all with advanced inverter requirements. They're really big on sector coupling, linking electricity, heat, and transport, and using VPPs extensively. The Sonnen community is a great example there. Over 20,000 home batteries acting as a VPP, providing grid services, sometimes even more accurately than conventional power plants.
Sector coupling, that's an interesting angle. What about the UK? I know they're big on offshore wind.
They are, and they're integrating grid forming right into it. Hornsea 1, that massive 1.2 gigawatt offshore wind farm. It uses grid forming converters for its long 120-kilometer undersea cable connection. The wind turbines themselves provide synthetic inertia and voltage control. It's already proven itself during grid disturbances and even demonstrated black start capability directly from the wind farm. That's a potential game changer, especially for restarting parts of the grid remotely.
Black start from offshore wind.
Oh.
Okay. Now, shifting over to Asia Pacific, what's the picture in major players like Japan and China?
Japan's grid modernization, especially after Fukushima, is heavily reliant on this. They've got a 30% renewable target, which pretty much necessitates grid-forming support. They're focusing a lot on their isolated island grids as test beds for this technology, demonstrating quick restoration after disturbances. China's involvement is, characteristically massive. They have over 75 gigawatts of energy storage deployed already, with a growing portion having grid-forming capabilities. This is supporting their push towards over 40% renewable electricity generation. They're investing enormous sums, over $100 billion a year, in grid modernization, including grid-forming tech and developing the standards to manage it all.
And back here in North America, beyond Texas, California and New York are always interesting markets.
Right. California's grid operator, CISO, has been proactive. They mandated grid forming for new battery storage over 20 megawatts quite early on, setting specific performance standards. Moss Landing, that 400-megawatt system, is a key part of their strategy and apparently exceeding its performance targets. New York, particularly Conned in the city, is tackling the challenge of integrating grid forming into dense, complex urban networks. That means things like modifying existing network protectors to handle power flowing both ways, coordinating multiple units, and boosting restoration capabilities after outages. Crucial for reliability in a place like Manhattan.
Makes sense for urban grids. And finally, islands the Caribbean comes to mind. They face unique challenges. How's grid forming helping there?
Puerto Rico is the standout case study, especially after Hurricane Maria. Their recovery strategy heavily features grid-forming tech. They have over 50 community microgrids, often solar plus storage, with grid-forming capability. And they're planning 1.5 gigawatts of larger battery storage, again with mandatory grid-forming requirements. These systems provide local resilience, autonomous operation, black start. They actually kept the lights on in those microgrid areas during Hurricane Fiona in 2022. They've seen much faster restoration times, 75% faster, and avoided hundreds of millions, over $500 million in outage costs. The lesson for islands is stark. Grid forming is pretty much essential for stability in smaller, isolated systems. A distributed approach adds resilience, and it enables greater energy independence.
Okay, so we've toured the globe, Australia, Texas, Europe, Asia, islands, seeing these incredible applications. Let's pull it all together. What are the big takeaways for you, for the engineers listening, and for the industry as a whole? What's the future trajectory?
Well, the first big one is simply technology maturation. This isn't theoretical anymore. The real-world data, whether it's Australia's frequency response being 50% better than models predicted, or Texas batteries hitting incredible accuracy levels, it shows the tech works, and often better than expected. Second is the economic transformation. Grid forming isn't just a cost, it's an economic advantage now. It earns premium payments in markets. It allows utilities to defer billions in transmission upgrades. That fundamentally changes project economics and grid planning. And third, maybe counterintuitively, is operational simplification. There were fears this would make grids harder to run, but the reality with proper controls is that high renewable grids supported by grid-forming assets can actually be more predictable and manageable than grids dominated by legacy thermal plants.
More predictable, that's a fascinating point. It flips the narrative a bit. What about the market side of things? How's that evolving globally?
We're seeing rapid market evolution. There's definitely a trend towards regulatory convergence standards like that Australian one, ASNZS 47777.2, are influencing rules worldwide. That helps everyone. Commercial viability is also clear now. It's moved from being maybe a compliance item to a competitive edge. VPPs are creating totally new revenue streams, and the supply chain is caught up. Major inverter manufacturers now offer grid-forming capabilities almost as standard. It's becoming much easier to specify and deploy.
So the ecosystem is developing. Okay, last point, but maybe the most important for our listeners. The engineering implications. What does this mean for engineers on the ground, for careers?
Yeah, this is critical. Success hinges on engineers who get both power electronics and grid operations. Those traditional silos are breaking down. You need people who understand how these smart inverters interact with the wider system. The whole design philosophy is shifting too. We're moving away from just figuring out how to accommodate passive renewables towards designing renewable systems that actively support and strengthen the grid. That's a big mental shift, and what that means is, honestly, unprecedented career opportunities. If you can operate at that intersection, power electronics, grid ops, renewables, you're going to be in very high demand. It's a really exciting space to be in right now.
Absolutely. What an incredible deep dive today. It seems clear grid-forming technology isn't just a niche solution anymore. It's proven itself as foundational for high renewable penetration and, maybe more importantly, for creating grids that are fundamentally better, more resilient, more efficient, more economical. So the question for you listening isn't really if this tech will reshape the grid, but maybe how quickly it's going to happen where you are and whether you'll be part of leading that change or watching others do it first. Tomorrow, we'll build directly on this. We'll explore how this transformation is impacting engineering careers, potential salary premiums, and the specific skills that utilities and developers are looking for. As always, if you'd like to leave feedback or have questions, please do reach out to our producer, Julia Squay, on LinkedIn.